Hi, Cynthia, do you hear me?
Yes, I do.
Okay. Thank you for joining us. I gather you are in California. I'll make some introductory remark in Korean for a couple of minutes and I'll ask you to speak. 오늘 세미나를 시작을 하겠습니다. 저희가 그 올해 웨비나 시리즈로 하고 있는 행사의 어떻게 보면 하이라이트인데 키노트 스피치입니다. 오늘 행사 진행을 맡은 서울대학교 고학수라고 합니다. 뭐 이제 몇 차례 쭉 오신 분들도 계실 텐데요. 그 서울대학교 인공지능 정책 이니셔티브에서 매년 인공지능 영역 국제학술대회를 하고 있었는데 올해는 코로나로 인해서 이렇게 웨비나 형태로 외국 분들 초청을 해서 세미나 시리즈를 진행을 하고 있습니다. 뭐 당연히 이제 장단점이 있겠는데 웨비나로 해서 오히려 그 연사 말씀에 집중하게 되는 그런 장점은 또 확실히 있는 것 같습니다. 그 오늘 키노트 스피치를 해주실 Cynthia Dwork 교수님 간략히 말씀을 드리겠습니다. 그 컴퓨터공학 전공을 하신 박사님이고요. 오랫동안 그 연구자로서의 정체성도 있지만 동시에 기업 현장에서 활동을 하셨었고요. 그 데이터의 활용도가 높아지는 와중에 프라이버시가 중요하다라는 인식을 다른 분들보다 훨씬 일찍 하시기 시작을 하고 고민을 많이 하셔서 이 데이터 비식별 영역에서는 단연 전 세계적인 선구자이십니다. 그 중에서도 특히 그 Differential Privacy라고 뭐 한글로는 그 뭐 흔히 차분 프라이버시 뭐 이런 정도로 쓰이는 것 같은데요. 그 Differential Privacy 개념을 처음 창안을 해내신 분입니다. 한 15년 정도 됐고요. 그 이후로 이 개념이 계속 리파인이 되고 기업 현장이나 실무 현장에서도 응용이 되고 있습니다. 뭐 기업을 떠나서 최근 몇 년에는 미국 센서스에서도 그 이번 올해 그 센서스 조사를 하면서 디퍼런셜 프라이버시 개념을 이제 직접 본격적으로 도입을 하고 있는 중이고요. 그래서 실제 지금 현장에서 도입이 되면서 여러 가지 또 실무적인 이론적인 챌린지들이 나타나고 있습니다. 그래서 오늘 말씀은 이제 이 디퍼런셜 프라이버시가 어떤 것이고 지금 어떤 상황이고 앞으로 어떻게 될 것 같은지 뭐 그런 맥락의 말씀을 드리겠습니다. 이분은 컴퓨터공학을 전공을 했지만 이렇게 프라이버시 문제를 포함해서 사회 전반의 문제 또 공정성이나 차별과 관련된 그런 잠재적인 위험성 이런 거에 관해서 계속적으로 고민을 하고 계신 분이고요. 그래서 제가 흥미롭게 여긴 것 중에 하나는 이분이 미국의 그 과학할리먼 회원이기도 할 뿐더러 공학할리먼 회원이기도 하고 철학소사이어티 회원이기도 하고 미국 학술원 펠로우이기도 하고요. 그런 그 정말 영역을 넘나들면서 인정을 받고 있는 뭐 그런 이제 그 정말 21세기형 융합형 속학이시고요. 뭐 그 몇 년 전에 하버드를 옮기신 후로는 페어니스에 관해서 연구를 많이 하고 계십니다. 그리고 최근에는 뭐 줄줄이 기다렸다가 상을 계속 여러 가지 상들을 받고 계신 중이고요. 뭐 이쪽 영역을 들여다본 분들은 반드시 거쳐가야 되는 그런 분이라고 말씀을 드릴 수 있겠습니다. 이 오늘 스피치를 좀 길게 준비를 하셔서 아마 한 50분 정도 말씀을 하실 것 같고요. 끝에 그 Q&A 시간을 그래도 어느 정도는 갖도록 하겠습니다. 그래서 질문이 있으신 분은 채팅창에 올려주시면 그 하여튼 시간이 되는 한 질문을 제가 전달을 해서 진행 끝부분에 그렇게 진행하도록 하겠습니다. 말씀을 청해서 듣도록 하겠습니다. Cynthia, so now it's your turn. You can now start.
Okay, I'll share my screen now. So thank you very much, Professor Ko, for the introduction, for inviting me, and thank you to the members of the audience for joining me for this discussion of differential privacy. So let me start by summarizing the talk. When we think about privacy preserving data analysis, it's important to differentiate between two kinds of analyses. The first is trying to get a statistical understanding of your population as a whole. So for example, this is what we do with census data. Or perhaps we are analyzing loan data for evidence of systematic discrimination. Or maybe we're even running machine learning algorithms to train a classifier to distinguish images of healthy brain cells from cancerous ones. So this is the first statistical understanding of the population as a whole. In contrast, we might have what we call finding a needle in a haystack, as in the Total Information Awareness Program that was aimed at finding terrorists. Differential privacy is for the first kind of analysis. It is simply the wrong tool for finding a needle in the haystack. If you need to find the needle in a haystack and somehow want to give privacy to everybody except the needle, I don't know how to do it. Differential privacy is not the right tool for that task. So statistical data analysis, when we think about statistics, they feel private in an intuitive sense. So a statistic is a quantity that's computed from a sample, and it tells us about the population as a whole. Now, one of the reasons that they feel private is that if we had two different data sets that were collected independently from the same population and using the correct methodology, then they should tell us more or less the same thing. And so our sense of privacy derives from this fact. Essentially, nobody knows if I am in the sample. I could claim I opted out. Maybe it was an entirely different sample and I was never even invited to join. And in that sense, it is not, the things that are learned from the sample are not strictly about me. So this intuition that statistics sort of should do the job is not a bad intuition. And in fact, it's on the right track, but it needs help, as we will see. And differential privacy provides exactly this help. Moreover, differential privacy preserves this sort of statistical feeling of privacy for all computations, including this I could have opted out semantics for every computation, including total population counts. Okay. So how do we abstract the problem? Because I'm a theoretical computer scientist, and we've seen many, many attempts at privacy preserving statistics that haven't worked. How did we abstract it so that we made some progress? So the dream in this work, which was begun in 2002, is to permit the analysis of a data set while preserving the privacy for all of the individuals in the database. We abstract it as follows. We have on the left the database, which contains lots of very sensitive information about many different people. And we have on the right a data analyst. And the analyst makes what we call queries to the data set. So the analyst asks a query Q1 and gets an answer A1. And then perhaps depending on the answer to that first query, the analyst will revise her query, refine and ask another question Q2, and then get an answer A2, and so on and so forth, back and forth. Now, this is very stylized, and it's a really broad abstraction, and it captures the actions of multiple data analysts who have run one study, let's say call it Q1 by analyzing the data and producing outputs A1, that are then followed up by other studies, Q2, Q3, and so on. And it even applies, this abstraction is very broad, it even applies to the creation of synthetic data that in some sense look like real data and mirrors the statistical properties of the real data, which somehow, though, are created in a privacy-preserving fashion. Always when we were doing this work, from the time we began in about 2001, the census was the driving scenario. For us, the census represented analysis of the people's data for the benefit of the people, with a legal mandate for privacy. It's very different trying to get people who have been working for a long time with no privacy requirement to pay any attention. But when people have a legal requirement for privacy, then the technology becomes of interest to them. The uses of census data include apportionment of representatives to the United States House of Representatives, the allocations of hundreds of billions of dollars in federal money, redistricting, and enforcing voting rights. So this is an example that we're going to be carrying through today, flossing your teeth. Some people floss regularly, some people do not, and some people may be embarrassed, especially about not flossing. So suppose that we wanted to say, well, we have a good intuition for what a statistic is, so why don't we just insist that the database only answer statistical queries, only provide broad statistics about large sets of people. And the problem with this kind of an approach, although I applaud the intuition, is that it is vulnerable to something called a differencing attack. So if we had the answer to the following two questions, how many living physics Nobel laureates floss regularly? And how many male living physics Nobel laureates floss regularly? With those two pieces of information, we can subtract one from the other, and we can determine whether or not Donna Strickland, the only living woman physics Nobel laureate, flosses regularly. Now, this differencing attack is just one example of how seemingly innocent queries over large sets can be combined to compromise privacy. More generally, there is what we call the fundamental law of information recovery or information reconstruction, which states that if we're given overly accurate estimates of too many statistical queries, then the result is blatant non-privacy. We can completely destroy privacy. Now, the reason I have these terms in quotes is that what overly accurate means depends on how many statistics we want to be able to answer. If we want to be able to provide a very, very few statistics, then we can be pretty accurate. If we want to release many, many, many of them, then the accuracy has to deteriorate. This is a mathematical law. This has nothing to do with any specific kind of attempt at privacy, almost any definition of privacy, and it's just sort of a fundamental limit that we have to live with. Now, one of the consequences of this is that we can't just release a synthetic data set in some magic way that will permit accurate answers to all possible future queries, because if we did that, then we would be providing something that would give overly accurate estimates of too many statistical queries, and that would be blatantly non-private. And as a result of this insight, we began to think more in terms of a query response scenario where the only statistics that are produced are ones that are explicitly requested. Okay, good. So now let's get to the definition of differential privacy, starting with motivation. So again, the goal is privacy-preserving data analysis, and we need to say, what do we mean by this? Because without a proper definition of privacy, we literally don't know what we're talking about. This is a picture of Cecilia Helena Payne-Gaposchkin. She was among the first women to obtain a PhD in astronomy, and she was the first person to obtain a PhD in astronomy at Harvard. And she's famous in part for having ascertained the temperatures of the different classes of stars and estimating the great abundance of hydrogen in them, much more than there is in Earth, while doing research for her dissertation. And that contradicted the belief at the time that the sun and the Earth had similar composition. So our question is, here's a database. It contains personal information about pain, what is the kind of protection that we want to offer her? So a natural candidate, and certainly the one that I first tried, was articulated by Tordelinius in 1977. He was a statistician interested in what he was calling statistical databases. And what he says is that the data analyst shouldn't learn anything new about pain based on the interactions with the database. So for example, Payne might be an extrovert and publish all sorts of things about herself on the web, and that's fine, but we don't want to punish the statistical database for revealing the things that Payne herself actually published. But the analyst shouldn't learn any more about Payne. Okay. So this is very natural. If any of you know anything about cryptography, this is an analog to what's called semantic security for a crypto system. The problem with this definition is, if this is our goal, then what is the point? So let's assume that I am from Mars, and I believe that all humans have 2 left feet. And in particular, I believe that Cecilia Payne-Gaspachin has 2 left feet. And then I interact with the data set, and I learn that the vast majority of humans have 1 left foot and 1 right foot. So now my belief about Payne has changed, and I think it's very likely that she has a left foot and a right foot. I have learned something about Payne that I had not known before I interacted with the data set. And the question that we have to ask here is, have we compromised Payne's privacy? And the answer there is, well, we get to decide. Do we call this a privacy compromise or not? Ideally, we would learn the same thing even if Payne is replaced by another random member of the population. So this is Henrietta Swan Leavitt, who was the first to note a relation between certain variable stars' peak brightness and the period over which their brightness varied. And this proved to yield a valuable means for measuring distances across space. So we took the position that this was not a privacy compromise for Payne because we would have learned the same thing if Payne had been replaced by Swan Leavitt. And that's the heart of differential privacy. What it says is that the outcome of any analysis should be essentially equally likely, independent of whether any individual joins or refrains from joining the data set. That's getting back into the I could have opted out privacy semantics. That's the English language definition of differential privacy. So in a little more detail, imagine now that our data analyst actually knows a whole lot. The analyst knows the entire database, including all of Payne's data, and that's one scenario. Yes, so she knows all of that. And she also is told that she is either interacting with the database that has Payne's data or the database but with Payne's data now removed. And her job, knowing all of that, is to try to guess which of these 2 worlds she is in. With which database is she interacting? The larger one that contains Payne or the smaller one that's just like the larger one but doesn't contain Payne? And differential privacy is going to require that even such an analyst shouldn't be able to tell which database she's interacting with. Okay. Not only that, unless specific information is leaked from the database itself, such an adversary would never be able to distinguish. So when we say that the outcome of an analysis is essentially equally likely, that suggests that there's some uncertainty in the probability with which a particular output is reached. Where is that uncertainty coming from? The answer is it's coming from coin flips the algorithm itself introduces. So we always are talking about a worst case scenario over all databases. The uncertainty is not coming from the database. It's only coming from the behavior of the algorithm. And that's important because we control the algorithm. We are the good guys. If we tell the algorithm to flip coins, it flips coins. So to get a little bit more intuition about essentially equally likely, imagine that we have two coins. One coin is exactly a fair coin. If we flip it, its probability of coming up heads is 1/2, or let's write that as 500 over 1,000. The biased coin is almost like our fair coin, except instead of having probability 500 over 1,000 of coming up heads, it has probability 501 over 1,000. Now, given one of those two coins, this algorithm, which we can call the flipping algorithm, will flip the coin and produce either heads or tails. And we can see that the probability distribution on outcomes is nearly the same for the two coins. And in fact, given just one or even several flip outcomes, one can never determine which was the true coin. We would have to get to something like 1 million flips before we would start to have any sense of certainty as to which coin was being flipped. So that's what we mean by essentially equally likely. The probability distribution on outcomes should be very similar when pain is versus is not in the data set. Now, that's a very, very strong definition of privacy. And one might be tempted to think that, okay, you can have privacy, but how can you possibly do any meaningful data analysis? And it's very interesting to note that this requirement that small changes to the database shouldn't have a big impact on the probability distribution of the outcomes is what we call a stability property. The outcome distribution is stable to small changes in the data set. Now, we'll be using stability to preserve privacy, but it's well known in machine learning circles that stability is necessary in order to prevent overfitting. That is, in order to arrange that an algorithm that you train on a training data set will in fact work well when you get to the population from which your training data set was drawn. And so while we often think of privacy and accuracy as being in conflict, this is a sense in which privacy and an important aspect of accuracy, known as generalization to the larger population, are actually aligned. Okay, now I'm about to tell you the formal definition, the mathematical definition of differential privacy. This is essentially the only math you're going to have in the talk. But it's important to get the flavor because there are one or two details that are very unfamiliar. So first of all, we call our algorithms mechanisms, and we usually call them M. So we're going to talk about an algorithm M for data analysis. Now, differential privacy isn't an all or nothing proposition. Differentially private algorithms are equipped with a measure or parameter, usually called epsilon, denoted here, which is going to be a maximum amount of privacy loss. So that's what our epsilon is. And those are the pairs of data sets we've been seeing until now. We have data sets X and Y. They're identical, except one of them is larger than the other, and it contains the data of just one additional person. In our example, that was the data set without pain and the data set where we've added pain in. Okay, finally, we have to look at possible output events. These are things that the algorithm can produce. And the requirement says simply that the probability that we see a given output event S, when the algorithm M is operating on X, is bounded by, and I'll explain this quantity in a minute, e to the epsilon, times the probability that we see the same outcome when the algorithm is operating on Y. So differential privacy bounds the ratio of the probabilities of an event on any pair of neighboring databases. And the algorithm in particular gives epsilon differential privacy if this value of epsilon fits in here for the equation. So our probabilities here, as I said earlier, are over the randomness that is introduced by the algorithm. And the value epsilon is an upper bound on the privacy loss, something formal called the privacy loss. So when epsilon is a small number, e to the epsilon is approximately 1 plus epsilon. So suppose epsilon were 0, then this would just be saying that these two probabilities are equal because the roles of x and y are symmetric. So the same inequality has to hold even when we swap x and y. But of course, if we can't tell any difference whatsoever ever when we change the database, then you can argue that there's absolutely no information. That sort of the all zero database has to give rise to the same distribution and outcomes as the all ones database. In differential privacy, we allow a little bit of slippage, and that's captured here. So this is a statement, this differential privacy guarantee is a statement about the behavior of the algorithm. It doesn't care what the adversary or the data analyst knows, not now and not in the future. So in this sense, differentially private algorithms are future-proof. And this now says that, yes, you can learn something about pain, but you can only learn things about pain that you could have learned had she not been included in the data set. So that's the sense in which we are really protecting her privacy. Anything you could have learned about pain when she's in the data set, you can learn about her when she is not in the data set. This definition then lets us separate what is learned about pain from the teachings of the database as a whole, from what is learned about pain as a result of participation. It lets us learn that smoking causes cancer without compromising the privacy of any smokers, or for that matter, any non-smokers in the data set. No one need worry that their insurance rates will increase as a result of participation in the data set or in any medical study if the data are protected using differential privacy. Okay. Finally, differential privacy affirmatively hides the needle. If X is the database including the needle, and Y is the database, is the haystack without the needle, then differential privacy says you can't tell whether you're interacting with the haystack or the haystack without the needle. So you certainly can't find the needle in the haystack. Differential privacy was actually designed explicitly to protect the outliers, as they are often the most in need of privacy protection. So there are certain properties that flow from the definition of differential privacy, independent of how it's actually implemented. There are many, many different differentially private algorithms for various tasks, and they all have these properties in common. As we said earlier, they are future-proof. They're resilient to present and future information from other sources. Another very important property is that we say differentially private algorithms compose. And what that means is, while every differentially private interaction leaks a tiny bit of privacy, we can understand how privacy losses accumulate when we do many different computations on the data. And in fact, at worst, those losses add up. So we can analyze the cumulative privacy loss when we want to do many questions, but also this now lets us program. So the way programming works isn't just everything is a bunch of multiplications and additions, even though we know that all computer programs can be expressed as a sequence of multiplications and additions. Instead, people build what we call computational primitives or building blocks, and then they combine these in creative and clever ways to carry out more sophisticated computations. And usually in ordinary algorithm studies, the whole goal is to minimize the spending of some resource like time or storage in order to carry out the computation. So differential privacy now, because of this composition theorem, is programmable. We can define simple differentially private primitives or building blocks, and then we can carry out more complicated analyses by combining these little primitives in creative and clever ways. So this is unique. Differential privacy is the only method that lets us do this, and it's where we get all of our power from. So that's the definition of differential privacy and the key properties that derive from the definition. Let me tell you about one of the simple differentially private building blocks that has been very powerful. This is called Laplace noise addition. So suppose we want to know or release to the public in a privacy preserving way, what is the population of Washington, D.C.? So I got this from a Census website. According to the website, the population estimate on July 1st, 2017 was 601,723. And that was supposed to have been from a total enumeration. Of course, in reality, it's an estimate because the census workers do miss some people, especially young children, immigrants, and homeless people. So there's always, in fact, some uncertainty in the numbers, and we're going to add a little bit more in differential privacy, but in a systematic way. And for the purposes of this discussion, let's assume that the enumeration was perfect. So the true count, 601,723, it's illustrated here by this red star. And these are the numbers from 0 up to 1 million and so on. Now, suppose one person opted out. That would change the count to 601,722, and that's shown here by this star with the yellow center. So the intuition for this random noise addition is to add random noise that's going to obscure the difference between these two numbers. It's going to hide whether the actual count is given by the red star or the yellow star. So here I have a picture of a probability distribution over outputs when the count is 601,723. It's concentrated around the true answer, but neighboring answers still have some significant mass, and that's true for just one smaller, just one larger, maybe two larger, two smaller, and so on. Now here we have the distribution when the true count is 601,722. So those are the two curves, and we need that when the curve is the, my cursor's not working. When the curve is the one centered over the right star, there's enough mass over the left, over the yellow star. And when the curve is centered over the yellow star, there's enough mass over the right, the red star. So how fat should the bulges in these curves be? Well, the answer is, it depends on two quantities. One of them is how much the data of one person could affect the count. That's called the sensitivity, or delta. And you can see that the sensitivity is 1. That is, having one person opt in or opt out can change the count by at most 1. The other property that we need is, the other quantity that we need is how strictly do we wish to preserve privacy? Remember, privacy is not all or nothing. We can have a small amount of privacy loss, that might be an epsilon of 0.01, or a larger amount of privacy loss, an epsilon of 0.1. Those are the two key quantities, and the answer is the fatness, or the standard deviation, of these noise curves should be delta over epsilon. And let's just take a quick look at that quantity for a minute. If I'm trying to release in a privacy preserving way a statistic whose value can change a whole lot by adding or deleting one person, then delta is a large number and the curve has to be fat, it has to be wide. So there is delta sitting here in the numerator. Bigger delta means fatter curve. Now, if I want very good privacy, I want epsilon to be very small. And here's epsilon in the numerator. When I make epsilon small, the quantity delta over epsilon gets very big. And again, the curve would be fat. So this is the answer. And formally, this is the precise noise distribution. For us, B here is delta over epsilon. Okay, so that's your first technique. I want to briefly mention one more technique, which is because industry likes it a lot, so you should know what it is. This is called the local model, where intuitively we're going to roll privacy into the data before the data are collected. So if you have an Apple phone, this is what it's doing. If you've been using Google, this is what Google is doing. If you've been using Windows, this is what Windows is doing. The idea is we're going to add randomness to the raw data, not to the outcome of a computation, but to the raw data while it's still out on the client, on your phone, on your laptop, on your iPad. And then after the data have been randomized, intuitively rolling privacy in, then and only then are they collected by the server. Industry tends to like this because it pushes the trust boundary out to the client, and industry doesn't have to worry so much about privacy of the collected data because what's collected already has been made private. So here's just a quick example of how you might do something like this. Suppose we're the audience out there. I want to know what fraction of you flossed your teeth last night. So the way that we would do this kind of poll is, in this local model, is we would give you instructions. First of all, each of you independently should flip a fair coin and not tell anybody what the outcome is. If the outcome is heads, though, flip another coin, flip again, and say yes if the coin says heads, and no if the second coin says tails. So notice that in this particular case, if the first coin came up heads, what you say has absolutely nothing to do with your true data, whether you flossed last night or not. On the other hand, if the first coin comes up tails, then you answer honestly. And there's a quick privacy analysis that we can go through. This turns out to give us an epsilon that's approximately 1.098. And the key point is that you can reverse engineer the noise. Noise is added in this first case to learn the approximate flossing fraction. Okay. And the errors for the fraction, the errors will look like something like 1 over square root of n. So that's the local model. And here are some places in which differential privacy has been deployed. In the centralized model, Google and Facebook have COVID-19 mobility data. We'll see a picture of that on the next slide. But they were measuring things like the response to the work from home and stay at home orders. Microsoft uses it for Windows reporting and machine learning. For in Office, it's being used for predictive text language models, and in general for office workplace analytics, and so on and so forth. The local model, I think the big deployment of this was first done by Google in 2014 in what was called the Rapport project, and they're using it now for hundreds of analytics metrics. Microsoft is using it for Windows telemetry on user experiences. and Apple is using it in lots of different ways on your phone. There are also several industry platforms that are available for anybody to work with. There's Private TensorFlow by Google. Microsoft and Harvard are building an open source platform, some of which will be coming online shortly. There's Private SQL from Google, and DiffPrivLib from IBM, and Flex from Uber. So industry, I think, wants people to be playing with these things so that they'll become educated in the technology. And here's an example of, let's see, this one was from Facebook, change of movement in California counties. So I think each gray line represents the change amount of movement on these various different dates for different counties. And then this gold line, for example, is Trinity County, and this gold line is Tulare County. And this, I think, is Google's mobility data, also interested in how did mobility change after the stay-at-home and work-at-home orders. Good. Okay. So here we get to what I'm most excited about. This year, for the first time, the US Census Bureau will use differential privacy as its primary means of disclosure avoidance in the 2020 decennial census. And as I mentioned, census was the original motivation for our work, the allocation of hundreds of billions of dollars of the people's resources. And like voting, census is located at the very heart of representational democracy. And like voting, it affects long-term outcomes and the distribution of public benefits via the flow of federal dollars. It tells us which places are best served by hospitals, which places are best served by helicopters to get people to hospitals, which geographies are dense and are in need of on-the-ground resources and which are sparsely populated. The potential harms for privacy compromise in the census are severe. So for example, the discovery of a violation of what are called Section 8 subsidized rentals, this is housing assistance for which a family might have waited for years, can result in eviction and homelessness, a huge price for a family. And a government whose immigration and customs enforcement directorates have contracted with Palantir to find illegal aliens for deportation is surely capable of contracting for Section 8 and other zoning enforcement. This is my belief, for the political mileage no less than for the money saved. So why did it turn out that the census decided to use this? This is a picture of John Abowd, the Chief Scientist and Associate Director of Research and Methodology at the Bureau. And bluntly, Abowd argued that the techniques that were used up through the 2010 decennial census simply no longer suffice. That technical advances revealed a new vulnerability, allowing people to reconstruct data from tables that were previously assumed to be privacy preserving. Remember that fundamental law that overly accurate estimates of too many statistics is completely non-private? The Census Bureau released 7.7 billion statistics on 300.7 million people. So that turns out to be overly accurate answers to too many statistical queries. And the Census Bureau actually carried out its own reconstruction and de-identification attacks on the 2020 data release. And I'm not going to have time to go in detail into what they did, but there's a beautiful talk that you can hear on YouTube by John Abowd that was delivered in February 2019. And he outlines what they did, what they were able to attack. And he said, this is not okay. This is not acceptable. They were able to compromise the privacy of 52 million people using new methodology in the database reconstruction attacks. and also the fact that there are very, very rich sources of data from industry, commercial data sets that are sold that can be used to aid in a re-identification attack. So those two combinations were basically lethal. Okay. And the Census Bureau takes it seriously. So every Census Bureau employee, this is from their website, takes a lifetime oath to protect your personal identification. Disclosing any information that could identify you or your family means 5 years in prison or $250,000 in fines or both. And Aboud says, we fixed this for the 2020 census by implementing differential privacy. So great, I was happy. Were people in general happy? Maybe not. So people objected. The old private, especially researchers, for example, who make a living by analyzing demographic data from the census, said, hey, the old privacy protections worked well. Well, they might have worked well, but they don't work well now. They said the law doesn't care what you learn about people, only whether or not you can match a record to a name. There are people who said, well, we've heard a lot about the privacy budget, but we need to hear explicitly what you're doing about utility, because there is an accuracy privacy trade-off. Overly accurate estimates of too many statistics is blatantly non-private. So these are some of these are very legitimate concerns, and the principal challenges then could be summarized as follows. Researchers, historians, sociologists, demographers, economists are not trained to interact with data in a differentially private way. Moreover, for technical reasons which have nothing to do with differential privacy and everything to do with inner workings of the software at the Census Bureau, data are post-processed in a way that has no implication on privacy, but it creates a synthetic database that has only non-negative and integer marginals. And this introduces a statistical bias, which can be harmful in certain cases. Now, they don't have to do it this way, but in terms of legacy, it will take a while till they can change what they're doing. In addition, analysts need to be trained to adjust for noise. With differential privacy, you can adjust because the noise generation mechanism is known. That's a strength of the discipline. But it takes training and it takes research, and we're not there yet. And finally, there's no getting around the fundamental law. It is a law. It's a mathematical guarantee that has nothing to do with differential privacy. Finally, I want to make a claim that there was a picture that people had, and this picture kind of follows this gold-colored curve, and it says, there's a privacy utility trade-off. We get great utility if there's no privacy. There's a sweet spot in here where we get utility and privacy. And if we have too much privacy, then we will destroy utility completely. And I don't think this picture, that gold curve, I don't think it's the right curve. And I think that if you speak to anybody in official statistics, they will tell you that if you don't guarantee confidentiality, then people will not provide their data. And the real curve looks something like this blue curve, that the people who have nothing to hide, they may reveal their information when there's no privacy, but the people who are marginal in one way or another, they don't get to trust the same way, and they might not be willing, they will not be willing to release their data if proper privacy protections are not being provided. So I think the curve looks something more like this blue curve. And this was drawn by one of my students, Tasha Schoenstein. And just one more final slide before our reprise. There are two quantitative decisions that have to be made but they're policy decisions. So one of them is, I've said that differential privacy allows us to understand and control the cumulative privacy loss. Who decides what is the ceiling on this cumulative privacy loss? So how and who chooses the cumulative privacy budget? And once you have done this, there are many, many ways of taking that budget and apportioning pieces of it to different queries. How do we prioritize so that the most important queries that have in some sense, very small numbers will get prioritized, and they can use most of the privacy budget and take advantage of the extra accuracy that that gives? How do we prioritize the spending on different queries? These are social and policy questions. Whatever the social and policy people say, technologists can make it happen. But the technologists should not be setting the policy by themselves. So again, this talk in a nutshell, the intuition behind privacy of a sample is on the right track, but it needs help. Differential privacy provides that help. Differential privacy turns every calculation into a statistic with opt-out semantics. Differential privacy hides the needle, and it reveals the population as a whole. Thank you for your attention.
Okay, thank you. Well, I think it's very succinct presentation, and the people who had some vague knowledge about differential privacy perhaps learned a lot. Those of you who haven't even heard of the term might have learned some, but still not very easy to get a hold of it. There's one question from the audience. I'm not sure if you can see it from your side.
I see it.
Okay, I'll read the question in any event. My intuitive take, therefore probably wrong, is that these excellent properties of differential privacy is hard to achieve for small data sets, which are sometimes inevitably used by small and medium-sized companies. Would you tell a bit more about that aspect?
Certainly. So when we were developing this, we were thinking in terms of internet scale data sets, 500 million users, for example. And much to our surprise, the techniques have ended up being useful for much smaller data sets than that. There will be, think about statistics in general and think about machine learning. In places where you have enough data to do machine learning, you have enough data to do differential privacy. But it's a constant challenge how far down you can squeeze that. Now, here is one reason why you must absolutely be correct. Differential privacy is guaranteeing more or less the same distribution on outputs when the data set changes a little bit. If the data set is very small, then changing a little bit can correspond to changing almost the whole database. If the database is very large, then changing a little bit is precisely that. It's changing a tiny fraction. So it was designed for large-scale data analysis, and your intuition is correct, but it seems to be working at much smaller numbers than we originally anticipated.
One question perhaps related to the question that you just answered. I mean, you gave examples of the companies like, Google and Apple and Microsoft, which have been using and deploying the concept of DP. And I wonder if that shows the need for having enough of resources, whether just personal expertise or computational resources. How would you accommodate, or how would you give advice to smaller companies which may not have enough of resources?
Fantastic. So not everybody can afford to hire an expert in differential privacy. That's the complaint. So this is, of course, a problem. When you have a new technology and you don't have enough people who are trained in it, how do you get it adopted? The public platforms can be very helpful, and the Open DP, Open Differential Privacy community that is sort of centered at Harvard, led in part by my colleague Salil Vadan, is specifically dedicated to developing tools that can be used by non-expert researchers. And there are some things that you could actually go and start playing with right now. So look for the Privacy Tools Project at Harvard and get a glimpse of what there is. But libraries are one thing, and experience working with them is something else. And I don't have an automatic way to bridge that.
Okay. There is one more question, perhaps related to the fundamental concept of DP. The question is, one problem I see is that some companies may have additional information that can be applied to differential privacy data that hide the key information, or identifiers may be reverse engineers. How do you deal with this issue?
I'm not entirely clear about, I'm not entirely sure that I understand the question. I can see at least two interpretations of it, so let me respond to both.
Okay.
One of them is that you're talking about a company that has a data set and also has some extra information. And then I'm not quite sure what you're concerned about. If the company has the union of the stuff in the database and the other, then they have all that information. If you're saying that one company is using differential privacy on its data and another company has extra auxiliary information that has identifiers and so on, we don't care. Differential privacy doesn't care what that other company knows now or in the future. It is future-proof. It's completely robust to external information. So that's, since I don't fully understand the question, that's the best I can do. Oh, okay.
Yeah, it says this. The question was the second case you explained.
Great.
The next question asked about the U.S. Census. When do you expect to have a reasonable idea of whether DP worked well for the current year census?
That's a great question. At the moment, I'm so worried about the U.S. Census in general that differential privacy is the least of our problems. With the president trying to suppress from the counts, from the reapportionment counts, the illegal immigrants, with the Bureau having mysteriously changed its enumeration period from ending October 31 to ending September 30th, so that they will wildly undercount the population. I think this is going to be orders of magnitude worse than any errors introduced by differential privacy. If the enumeration were in fact carried out correctly, then I think we would know pretty soon what kinds of things work well in the census questions, in the census statistics, and which ones don't. There are certain artifacts that come from insisting on releasing synthetic data, which is non-negative. That has caused some problems for certain communities, especially AIAN, American Indian and Alaskan Native. and the Bureau has been modifying their algorithms a little bit to do better there. And we'll see soon, I hope, how well that works.
The next question is about teaching, say, letting the regulators understand how it works. I mean, differential privacy intuitively not easy to understand for the people who are outside of this, computer science world or statistics. And to give some sort of flavor in the context of Korea, a few years ago, the regulators tried the concept of K-anonymity. And the concept of K-anonymity was more intuitively easy to understand and appealing to the regulators, but it didn't really work well. And right now in Korea, we introduced in the law concept of pseudonymized data, which is a subset of personal subset of PII. And the question on the chatting room is, how can regulator reflect the idea of DP in the data protection regime? It can be too difficult for them to understand and incorporate the concept in the regulation. How do you respond?
I think it's better to invest in figuring out how to explain it than to use techniques that don't preserve privacy. I've done my best, but there are people who may be able to do a better job at this. There is, for example, a beautiful exposition of the idea of differential privacy that was published by Ed Felton at Princeton when he was the Chief Technology Officer of the Federal Trade Commission. So if you search for his blog on differential privacy, his blog post as CTO of the FTC on differential privacy, it's fantastic. So maybe, this task should be turned over to people like Professor Felton, who might be able to better communicate it, but it's not impossible. I've seen it done well.
Yeah, that's a very good answer, but at the same time, the person like Ed Felton, it's a real rare commodity. The people like that sort of expertise and also communication skill, that's very uncommon to see.
Yes, but the blog post you can read now, even though he hasn't been in that job for years. It's still there. Something written, videos.
Okay. The next question is more technical. I read in the PPDP, privacy preserving data publishing, that is in the complete data disclosure model. Is it possible to apply differential privacy to any numerical attribute value in the formal data set? If possible, for example, what kind of attribute could you apply to?
So I'm not sure by what you mean by complete data disclosure model. In differential privacy, we never release raw data. If you did, then you could imagine two data sets that differ only in the data of one person, and you could tell definitely which of the two databases is being used according to whether you see the raw data of that person. So I'm sorry, I don't know what you mean by the complete data disclosure model, but it doesn't sound compatible with differential privacy. Please go ahead and type into the chat a clarification if you like.
Okay. And the next question, what are the possible applications in the government sector or private sector?
So in the United States, there are many federal statistical agencies that gather statistical information on a huge range of topics that are not covered by the census. So, you know, agriculture and health and so on. So it is broadly applicable in those settings of official statistics.
And my own question, toward the end, you talked about the role of the regulators or discussions to be made in the policy arena. In particular, in terms of making determination about the value of epsilon or privacy laws. I mean, private companies perhaps make their own decisions, but in the public sphere, when you have to make a decision as to the value of epsilon, how would you make proposal to the public sector? Who makes determination or what kind of process? You know, whatever value you give to epsilon, there are bound to be debates.
Oh, you're absolutely right about that. Whatever value you give to epsilon, there's bound to be a debate. And, you know, I can only hope that one gives the maximum possible privacy conditioned on being able to actually use the information. But if you can't use the information without compromising privacy, you have a fundamental clash of goals. And that's, again, a policy decision. Now, we don't really know what large values of epsilon mean. They, in some sense, they may mean very little, but even a large value of epsilon will rule out, say, K anonymity, and it will rule out many mistakes that people could make. So there's a paper that I have discusses what we call an epsilon registry. The idea is that when companies and agencies use differential privacy, they should make a public statement about what is the value of epsilon, over what time period are they burning through their epsilons? Are they using an epsilon of 1 every single day or every fortnight? Or is it 1 over a period of 12 years? And so what we propose that people start building a knowledge set that tries to give some, tries to build up some experience that can inform others, because we don't really understand. We know that a very small epsilon is very protective. So a small epsilon is a happy epsilon, but large epsilons are unhappy after their own fashion.
The next question is about the applicability of DP, concept of DP to group privacy context. Have you, I don't know whether you have thought about it.
Yes, yes. So we understand the math for group privacy, and the privacy guarantee will, of course, fall as the size of the group grows. So what we would like is, and in some sense, it has to be this way. As you change a larger and larger fraction of the data set, you do want it to become clear that the statistics of your population are changing. That's appropriate. So we want that for small changes, you shouldn't be able to detect it, but for larger changes or large group privacy, well, you would start to see a difference. So, you know, we know the math for this particular approach. If an algorithm is epsilon differentially private, then for a group of size K, it is automatically, and without thinking, K epsilon differentially private.
Okay. I see 2 more questions. I think with these 2 additional questions, I think we'll have to finish. So the first of the 2, I read, how do you deal with smaller data set problems in DP? For example, in some data sets, there may be so few observations that some privacy is lost. how do you deal with such conflicts? Do you avoid giving information on those data, those cases?
Right. So the differential privacy guarantee is the same no matter the size of the database. And when the database is large, you retain utility. If the database is small, you would lose utility. So let's take the extreme case where the database has size 1. You want to lose utility completely there. You want to maintain absolutely the privacy of this one person in your data set. And so, you know, as it grows, as the data set grows, you get more utility for the same privacy loss. But you'll have less utility when the database is small. And that's by design.
Yeah. Okay. The last question. If BP is achieved in client before being collected, I believe it'll diminish the value of the data set and the things we can do with the data. Does the way in which we make the data set differentially private affect reusability or and/or possibility of, for instance, lambda may change in the future, delta may change in the future?
Okay. It is a theorem that you get more utility for the same privacy loss in the centralized case than in the local model. So I believe that in the end, everybody's going to move, even industry, you know, even big industries, I think they will move to the centralized model. This is based on just my guess. I have no inside information on this. And yes, the way in which when you make data private, think about it this way. Remember that fundamental law, overly accurate answers to too many statistical queries destroys privacy. Great. So when you make the data private, you better be targeting the ability to answer certain kinds of questions or certain questions, but you can't do it in a way that will allow you to answer all questions or too many questions accurately. So yes, you're absolutely on the right track, and I'm a big fan of the centralized model.
Then I'll give my own last question, which
Sure.
is, I mean, you just mentioned centralized model and decentralized model, and you know, with all the talk and popularity of edge computing and you know, the concept of federated learning, which is used by Google, I think that's one direction that the industry is heading. How would you compare DP or centralized model you were talking about as opposed to decentralized federated learning and that sort of models?
So they go together very well, that you can use cryptographic techniques to essentially act as if things are centralized when in fact they are decentralized. And the federated model sets itself up beautifully for that. So they go very well together, and it's an active area of research. Okay,
very good. I think with this, we'll complete the keynote speech. I'll finish in Korean a minute or two. 오늘 굉장히 많이 배운 것 같고요. 익숙한 분들도 계시겠지만 또 익숙하지 않은 분들한테는 이 개념을 처음 고안하시고 계속 고민하신 그런 내용을 컴팩트하게 들은 것 같습니다. 오늘 세미나 이렇게 해서 마치고 다음 주에 이제 다음 세미나가 이어집니다. Yeah, Cynthia, well, we are about to finish the seminar. Thank you for joining our seminar from the distance and your evening time in the US. We'll try to get in touch later on. And thank you.
Thank you so much for having invited me. It was a pleasure.
Okay, bye-bye.
Bye-bye.